Chile, from Santiago, and Sukhender will speak about hyperkähler, K3 derived, and something like this.
So first of all, of course, I should thank the organizers for inviting me here to this wonderful location. And as the last speaker, it's my pleasant duty to thank the organizers again for arranging the week for all of us in paradise. So, rainy paradise.
Rainy paradise.
The navel of the world.
The navel of the world, yeah.
The rainy navel of the world.
Well, it's better than paradise when the sun comes up. Okay, so I forget the title of the talk, but it had something to do with K3 category associated to hyperkähler manifold of K3n type. It's a bit of a mouthful. So the story starts with the following simple observation. Let S be a K3 surface over the complex numbers. So remember, this means that it's simply connected, kähler, and for us, what is most important that it carries a symplectic form. So H naught 2 is spanned by a symplectic form. So by Noether's theorem, it follows that, in view of all this, it follows that H1 of the tangent bundle, the dimension of this, well, this one can compute using Hodge theory, and this is 20. And finally, unobstructedness in this case, because H2 vanishes, H2 of D of S, same reason, is 0, it follows that the dimension of the Kuranishi space is 20. On the other hand, consider the Hilbert scheme of n points on a K3. So next, consider the punctual Hilbert scheme of n points on S. There is a tautological morphism from the Hilbert scheme to the nth symmetric product. So this is just the Hilbert Chow morphism, which just takes a scheme and sends it to its support. Studying properties of this, one sees that a couple of things. It's this Hilbert scheme is simply connected. Just as a K3 does, this Hilbert scheme carries symplectic form. And H2, the integral cohomology, can be identified with the following direct sums. It contains the integral cohomology of the K3 plus another generator, which is this is essentially 1/2 the exceptional divisor of C. 1/2 the exceptional divisor of C. Any manifold, which Kähler manifold, smooth, which carries a symplectic form and is simply connected, for us is going to be an irreducible holomorphic symplectic manifold, an IHSM. IHSM. So K3 is an IHSM, Hilbert schemes are IHSMs. In view of this last fact, the dimension of the deformation space, for exactly the same reasons, is 20 plus 1. One larger than the deformation space of the Hilbert scheme, the K3. So obviously what this means is that the general deformation is not a Hilbert scheme. So the question is how to describe it. In particular, where is the K3? So that's the question that we want to consider. I should just point out that I suppose in this deformation space, schematically, there are other loci which do correspond to K3s. These are other moduli spaces of sheaves on S. Moduli spaces of sheaves. But they're not nearly enough, of course. So this is the question. Before I explain some sort of an answer that we've arrived at, let me just say that the answer is categorical, which is what the title is. That what we try to do is to morally associate to each general deformation K3 category, which is the deformation of the derived category of the central K3. Yes. Okay. So let me explain how one might associate a K3 category to a deformation of the Hilbert scheme. So just consider, this is something very simple-minded, consider the universal family. Universal family. U, which spares X, C, such that X is in C, inside S times the Hilbert scheme. Q, these are the two projections. And let I sub U be the ideal sheaf of this universe. This gives rise to what's called an integral transform, a correspondence, which goes from the derived category of S to the derived category of the Hilbert scheme. Namely, given any object, you pull back, you tensor by this ideal sheaf, and you push forward. And as is customary, I've dropped all the L's and R's, etc. These are derived objects. Okay. So this is the integral transform with kernel. This is the terminology used. Let's C sub U the adjoint. So any integral transform with a kernel, just formally, and working with smooth manifolds, admits smooth projective varieties or smooth compact manifolds. By duality, admits such adjoints. So I won't write this down, but essentially you need to dualize this and shift. Here is a result which sort of gives you a key to how key to sort of thinking of or to associating to every possibly certainly to every Hilbert scheme the derived category of the K3 that it comes from, and is also the key to sort of extending this. So this is a result of Nick Addington, and also separately by Eyal Markman and myself. I should also have credited my co-author at the very beginning. So everything that I say here is joint work with Eyal Markman of UMass. So the result is that let A be the kernel of the composition C of U, phi of U, call it L. L goes from the derived category of S to itself. So the result is that this kernel A is a direct sum of shifts of the diagonal. 2 minus 2.
So you have a map of ds to ds now?
Yes, yes. So I'm just going this way and
back, projecting backwards.
Yeah, projecting back.
So and what is diagonal? How does it look?
So this is
okay.
Yeah. So this is an object of the derived category of S times S. Within S times S is of course the diagonal.
Yeah.
And these are A is just a sum of shifts of the structure sheet of the diagonal.
Oh.
So it's in particular it contains the kernel of the identity.
Yeah, I see. No, I didn't. Oh.
Yeah. So okay. So it's faithful in particular, but in a strong sense. It's strongly faithful. This is I'm referring to phi sub U. Okay. So in a sense, I mean, it's not entirely precise, but what this is saying is that the derived category of S is somehow embedded inside the derived category of the Hilbert scheme, but it's not faithful. It's not full. Excuse me. The embedding. Okay. So just a couple of remarks about this. First of all, I might say more about this if there is time. This phi sub U is what is called a Pn functor. Pn functor. I think n minus 1 in this case. And what this is due to Nick Addington. And what this is good for is it produces exotic autoequivalences. This gives rise to an exotic autoequivalence of the derived category of this hyperkähler manifold.
What means Pn functor? What do you mean?
Yeah. So a Pn functor is a okay. So it's the following. So maybe it's better for me to talk about a Pn object first.
Okay.
So a Pn object. P, let's say, in a derived category, is an object whose in X algebra is the algebra of a complex projective space.
Oh, okay.
And
in particular, a PN functor would be a functor which takes, an example of a PN functor would be a functor which takes the derived category of a point to, basically maps the structure sheaf of the point to such a thing. But they're generalizations. So you kind of see how this is happening here. In a sense, what is going on here is that there is a monadic multiplication. This object A carries some kind of a multiplication, and the multiplication is very much like the multiplication here. And there is a way to construct autoequivalences using these objects and these functors, which is like very reminiscent to how one constructs autoequivalences using spherical objects. Okay. So that's one. Two. We can, if I get to say everything that I intended today, it is not essential. It will follow that, in fact, a similar statement can be made for other moduli spaces of sheaves, M sub H V, using the universal sheaf or pseudo-universal sheaf in place of U. Provided here the Picard rank of the underlying K3 is not maximum. And so hopefully more about this. And finally, of course, when the dimension is 2, this is this functor happens to be an equivalent. This is a result of Mukai. So the proof here, just an indication. The way we do it is very straightforward, very natural. Addington is more clever; he does it geometrically. So the Hilbert scheme, by results of Mark Heyman, is what is called the Hilbert scheme of Sn clusters on S. This is the Hilbert scheme. So this is the moduli space which parameterizes orbits, essentially, of Sn. And by Bridgeland, King, and Reed, which is applicable in this case, it follows that the derived category of this Hilbert scheme. This thing is equivalent to the Sn equivariant derived category of S to the n. And this is much more combinatorial, so we transfer all of the calculations here. It's not so bad to compute. It's a computation.
But it is just the fact that you contract essentially rational varieties.
Sorry.
So going from symmetric power, from Gilbert scheme to symmetric power, you contract rational varieties.
It's traditional verb.
Rational varieties.
Yes, it's rational, but also to do with the fact that this is in fact a Krapin resolution.
Oh,
so the map,
so
yeah, so the map is semi-small. That is important.
Yeah, okay.
So sorry, semi-small. I should say. Okay. So the idea here, of course, is you replace S throughout with, this is the slogan, with the derived category of S, or the image of the derived category. That's what I'm saying. Okay, so how this is done is just explained in a simple example, just a toy example. Select, for instance, K be a field, and R be, let's say, a K algebra. You have a pair of, I'm going to describe a context which is similar to this. So you have you have two categories, the category of R modules and K vector spaces. And you have a pair of functors, just as you do here, going back and forth. So given an R module, you just forget. I'm going to call phi. And going the other way, you construct the free R module by tensoring with R. Call it psi. And in this case, psi is left adjoint to phi. You consider the composition, so let T be psi composed with phi. Goes from vector spaces back to itself. On a given vector space, this is simply tensoring with R, forgetting the structure. Okay.
So it's multiplication by number.
Sorry?
It's multiplication by number.
Basically, yes. I mean, this is so.
Dimensional part.
So this functor T that I've described here, this composition, in the same sense as the functor L that I've written down there, is kind of a monoid. Is a monoid, or more formally, monad. Yeah. What I mean by this is the following. So it has a unit map. This is just general nonsense. Which on any vector space, what it does is it sends it to, well, there's an obvious morphism from here to there, which is identity tensored with 1. So this is unit. And then it has what is called, it has a multiplication product. So a product would go from T composed with T to T. And all that this is doing is using the product structure in R to provide this map. So here it's identity followed by multiplication in R. You can define, the point is you can do all of this categorically, you can define T modules. So even though I'm writing everything down in this particular context, I should just emphasize that all of these maps are defined categorically using units and co-units of adjunctions. So you can define a category of T modules in vector spaces, which is simply the category of pairs V and H, where V, of course, is a vector space. And H is like an action. H is an action. What is an action? Well, it's the obvious thing, right? So whatever an action is, it should satisfy the following compatibility. So if you, for instance, if you multiply in T first and then act, that should be the same thing as first acting and then acting again. So this just says, so this is just a little exercise. I mean, this basically just asserts that V, for instance, times, excuse me, I mean, this is very simple-minded. V times xy is V acted on by x acted on by y. Right? So the consequence is that this category of T modules in vector spaces is equivalent to R modules. So it's exactly this kind of reconstruction that gives you what this image should be. So in our case, remember L was this functor that went from, excuse me, I think I didn't write it correctly. I wrote it as L earlier, but it should not have been written as L, excuse me. Okay, maybe I'll be a little, use the same notation but bold L. So this is the functor that goes from the derived category of the Hilbert scheme back to itself. And this is just composition in the other direction. So L is supposed to be T turned around, and this is essentially the same thing, except that here this is a comonad. So this is a comonad. Just the arrows get turned around, but the essential point remains that you can still construct a category of comodules, and it is equivalent in this case to the derived category of S. Okay. This makes use of the strong faithfulness, makes use of the fact that the composition in the other order was split, as I had written down there. Okay. Okay, so so now, I mean, it's clear what my task is. I have essentially described the derived category of S essentially in terms of the derived category of the Hilbert scheme together with this additional datum. So I just want to deform this. So let F be the kernel of the integral transform L. And in this case, the unit or the co-unit and co-multiplication, they appear as maps which go as in the following direction. So the co-unit is a map from F to the identity functor, correct epsilon, and the co-multiplication goes this way, delta. And this circle is just convolution, and our goal is to deform this triple, F epsilon. Okay, so let me say a few things about this kernel F, which is a pretty remarkable object. So a few properties which are relevant to us, the object F in the derived category of Sn times Sn. So F is first of all a two-term complex. So this fits into a triangle. So cohomology in degree 0 is just the structure sheaf of the diagonal in here. And there's an additional term like this. It's a two-term complex. This object E, it satisfies the following properties. First of all, E is reflexive. It is reflexive. I'll need these properties maybe later, so let's try to save them somewhere. Maybe here. So satisfy the following conditions. One, it is reflexive. Two, it is locally free away from the diagonal. In fact, so it's of rank 2n minus 2. And in fact, if beta is the blow up of the diagonal in Sn times Sn, then pulling back via this map resolves the singularities. So if this is the blow up,
So it becomes a buffer.
yes, blow up of the diagonal, and then the pullback of E mod torsion is locally free. And there are two other properties which, whose significance I'll explain in a bit. So first of all, it is omega slope stable for some Kähler class omega. In fact, it has been shown that by Markman, it's omega slope stable with respect to all omega. There's a condition 3 prime, which I'll write down in a moment. But 4, it is infinitesimally rigid. Which of course means that x1 of E with itself is 0. Okay. So what were 3 prime and 3 good for? I think before I proceed with that, let me just point out what the infinitesimal rigidity is saying. It's saying that, let's assume that we can actually deform. Now the goal is to say that everything really boils down to E. If we can deform E nicely, F does deform. And this rigidity is saying that it's essentially unique, which is great because we want to construct we want to essentially naturally associate a triangulated category to every holomorphic symplectic manifold, which should be the stand-in for the derived category of some non-commutative K3. The problem is that we want to deform not just F, but also the compatibilities. This is hard to control, so I mean, as you deform, it may well happen that these things get destroyed. One thing that you would like to use is, for instance, you might like to use the fact that these compatibilities hold, provided F deforms nicely, over the Hilbert scheme points. And it is true that Hilbert schemes are dense in the moduli.
All these boxes are full.
Look at the geometric construction of this F. Let's say these are all properties, yeah.
Yes, I mean these are geometrically they have to. One has to verify them very carefully.
Yeah.
I can say maybe a few things. Slope stability, for instance, depends very much on what the resolution is like. Namely, if you look at the blow up and look at the restriction to a fiber of the blow up, then this E restricts to it as to a symplectic bundle. So the fiber would be a projective space. It would be the complement of. You look at the tautological line, look at its complement mod L. So it relies very much on that fact. There are certain other,
Okay, I don't want to.
So it really does. One has to calculate. Okay, so 3 and 3 double prime. So whatever these are, they're essentially saying that E is hyperholomorphic, or truthfully projectively hyperholomorphic.
Okay.
This is a concept that was introduced by by Verbitsky. And what it says is this. So just some general facts. So given a Kähler class, class omega on an IHSM X, there exists a metric, emission metric G, such that the imaginary part of G is omega, the class of this is omega, and furthermore, G has holonomy, SBN. So what this amounts to saying is that there exist three complex structures, I, J, K, with respect to which this metric G is scalar. And this gives rise to what's called a twistor deformation. So this is a global deformation of X. So there's a family over P1. This P1 is just the sphere of these complex structures. And above every ABC is the corresponding complex structure, such that A squared, B squared, C squared, D squared. A sheaf is holomorphic or hyperholomorphic if it extends to this Kähler deformation. So this is something very transcendental, which I admit I don't fully understand. A sheaf V on X, let's say reflexive sheaf, is hyperholomorphic if V extends to a flat sheaf, script V over X. This is flat over P1, of course. And
so I understand that if you have, so in V you have basically three complex structures.
mm-hmm.
Yes, and then it has to be also kind of holomorphic with respect to all these complex structures.
Correct, exactly.
So therefore you have this very particular, there are not many of them.
You have very few of them, actually. So the only ones that are known are, in fact, things like the things which you can cook up using the tangent bundle.
Yeah,
And, in fact, this, up to this projectively business, the sheaf E.
yeah, and the sheaf E, can you cook it up out of tangent bond or some products, kernels, and so on?
Yeah, it's well, there is some. I mean, there is deformation theory hidden in this E, in the sense that it's the relative extensions. So you're on the Hilbert scheme. E is the relative x1 between restrictions of these between various ideal sheaves.
Standard.
Yeah. Okay, so the result is that V is hyperholomorphic, or omega hyperholomorphic with respect to an omega, if it is omega polystable. And the first Chern class of B and the second Chern class of B, they remain of Hodge type over the base, over the twistor base.
That's difficult. For C1 it's almost impossible.
Exactly, and in fact for E1 it doesn't. And that is the reason this is not hyperholomorphic, it's only projectively hyperholomorphic. So you kill, the only way basically you can do it for all, I mean, we want a deformation for all, in all directions.
Yeah.
So the only way to do it is to kill it. Exactly. So in our case, of course, C1 of E is not zero. But but the endomorphisms of E, this is hyperholomorphic. Oops. I can show is hyperholomorphic. And what is more, along these deformations, you also preserve the structure of, the algebra structure, the Azumaya algebra structure. And this is with respect to all scalar structures. And so this 3 double prime here is this condition that guarantees that this happens along all directions. And the condition is that C2 is invariant under a finite index subgroup of the monodromy group of Sn. This is what guarantees that it remains a Boston. Okay, a remark,
And it basically fixes it. Yes.
basically fixes it. So let X be an IHSM, it's the basic fact. Of K3n type. It doesn't have to be K3n type, this is true more generally. What this means is this is a deformation of a Hilbert scheme of a K3. Then, I shouldn't have said this, but this is more general. Then H2 of X carries a primitive symmetric bilinear pairing, non-degenerate.
Oh, I see. So it's plus of Q, yeah.
Exactly, but that, yeah, not degenerate pairing. I have to say this Q called Bovil Bogomolov Fujiki pairing. And essentially, the class of, I should keep this. That's okay. The class of E is made up of the class of this Q and the class of the tangent bundle. So in H4 of XQ, one has that C2 of ND restricted to a point. This thing is Q inverse minus C2 of the tangent bundle. I think times N minus. Okay.
What means Q inverse?
It's so Q lives in.
Yeah.
I mean, it's a form, so lives in H4 of Z dual.
I see.
Yeah.
Okay.
Okay. Yeah. So, I think rather than giving background, let me just state the theorem, and I'll let people ask questions. So, the theorem is that there exists a coarse moduli space M tilde parametrizing triples x, eta, k, where A is like and E. It's an Azumaya algebra. On x times x, sorry, I should have said that x here is an IHSM K3n type, so deformation of the Hilbert scheme, and eta is this is an isomorphism between H2 and a fixed lattice. So all of these spaces they have the same cohomology. The integral cohomology is isomorphic to a lattice lambda of, it's not unimodular, but it is 23 dimensional. 23 dimensional. It has signature 320, and the form that I'm using here is this form, the Bovil-Bogomolov form. The moduli space parameterizes triples. Pairs x eta, these are called marked holomorphic symplectic manifolds, and an Azumaya algebra on x times x, satisfying the conditions 1 up to 4 that are on this board. Two, the map, like a period map, M tilde, which goes to this quadratic Q. This is x squared equal to 0, x times x bar equal to 0 inside of P2, P of lambda sub c, which is this complexified lattice. So this map is simply the map which sends a triple to the Hodge structure on X. Right? So the Hodge structure on X on H2 is particularly simple. So we have two Hodge structure. It is completely determined by the complex line which is spanned by the symplectic form. This is via making use of the Bovil-Bogomolov form. Everything, the three components are orthogonal, and the other one is the complex conjugate. So this is simply taking X to its corresponding Hodge structure. This is a finite surjective local homeomorphism. Simple to show that it's a local homeomorphism. Surjectivity is hard. Any two points in the same fiber are inseparable. And 3, if x1 eta 1, excuse me, x eta A1 and x eta A2 are 2 points in a fiber, then A1, excuse me, and A1 and A2 are stable with respect to the same class. Then A1 is equal to A2. So this is kind of a version of Torelli theorem that was proved by Verbitsky, in the sense that this says that in fact this is generically injective. So there isn't a true Torelli theorem, but this is the best one can do. One can do something similar here. So for a while we didn't really understand this, but we'll just take 2 more minutes, and I think I'll stop. So I just want to say that very recently, Eyal Markman showed that it doesn't matter that you're a Hilbert scheme. If you have a sheaf which does satisfy all of these conditions, then in fact it is omega slope stable with respect to all Kähler classes. Yeah. So, in fact, it follows that so results of Markman say that if you look at the forgetful map from M, this is the moduli space of marked pairs, x eta. There is such a moduli space as well. Both of these map to this period domain. This is the forgetful map. Forget is an isomorphism. So, essentially, sorry, I should put components here. There could be more than one component. So, mark distinguished connected components. So the result is that there is, in a sense, a canonical association. Remember, we are deforming A. Associated to A is a monad object F, a comonad object F, and the category of modules over this is something like the derived category of a K3. So it's a K3 category. So this association is essentially canonical. That's the result. What is it good for? People might find it interesting to study this category. It might perhaps give some, I mean, we haven't done very much along those lines, might give a means of understanding the geometry of the hyperkähler a little bit better. But what, at least the proof, what it is good for is to produce some new autoequivalences. And this was the remark I made earlier, that the fact that in the Hilbert scheme case, the composition is split, in fact holds true for all moduli spaces based on K3s, whose Picard rank is not maximal, so less than 90, less than equal to 90. Okay. So that's all I want to say at the start.
Questions?
So essentially this bundle E is like some kind of bundle representation of Q. Yes. So you have the class, this totally unexpected class Q, yeah?
Yes.
And then it has this kind of bund representation. So you have a bund representative for this class. Just
correct.
Correct. Okay. Somewhat corrected, but
so you lift the class of Q to yes, a bundle.
Okay, if no more questions, let's thank Skender again.
The organizers once again.